Okay, so I wanted to start by telling you about my mistake from last time. That it was a very silly mistake. So basically, last time we did this example, we computed the Hilbert series for the monomial ideal, the square-free monomial ideal corresponding to a simplicial complex. And I drew the simplicial complex, and then I just wrote down the formula, and I told you you can do it, and it works. But the problem is that I just copied down the wrong simplicial complex. So the only thing is that I just forgot to shade in the triangle BCE. Okay, so the series that I wrote last time, I told you can do it, and that was the correct series for this simplicial complex. Okay. The camera is really okay. This simplicial complex. So this new green face I didn't have last time, and with this green face things work out. And last time things did not work out because we computed the F vector, and the F vector that we got was 1, 5, 9, 4. And that's because I did not put the green face, but the green face should be there, so I should have a 5 there. And now if I compute with my F vector 1, 5, 9, 5, I do this trick of Stanley, which you're going to explain in the homework why it works. You put the F vector here, you put all ones here, and then you start doing like Pascal's triangle, but with differences, right? So 5 minus 1 is 4, 9 minus 4 is 5, 4 minus 1 is 3, 5 minus 5 is 0, 5 minus 3 is 2, 3 minus 1 is 2. And so this is the H vector. So it's both. Combinatorially, it's the H vector for the simplicial complex. And then algebraically, it's the K polynomial for the Hilbert series. Okay? So that's that beautiful fact that this quantity has both a combinatorial meaning and an algebraic meaning. Okay? So this is my correction. And on the notes, it's written correctly. So you can just see what I did in the notes, and that's the correct way to do it. Okay? Okay, so having said that, let's keep talking about topology. I told you that my goal was to define homology groups for you, and we were on our way there. And you should think of this as how to find holes in a simplicial complex. It's oversimplifying it a little bit, but that's the basic idea. And so we were talking about this concrete example of a simplicial complex that we like very much. It looks like this. The triangle ABC is full, so ABC is part of the simplicial complex. The triangle BCD is empty. So I defined Ci, so this is delta, right? And I defined Ci of delta to be a vector space F to the I faces of delta. So I don't know, just to give you an example, C1 of delta consists of things of the form. So it's the F vector whose basis is given by basis elements labeled by one faces. Right? Now, when I say a one face, I mean one-dimensional. So one-dimensional means that I take the edges here. So the things here are of the form some constant times basis element AB plus some constant times basis element AC, etc. Where alpha, beta, etc. are scalars in my field. Okay? So that's my vector space. And what I'm going to do now is I'm going to define some maps. Okay? But I should just give you a terminology that the things that live in this guy are called the I-chains. Okay, so an I-chain is an element of Ci. Elements of C sub I of delta are called I-chains. For example, a zero chain is something like, I don't know, E sub A plus 2 E sub C minus E sub D. Right? Okay. So now what I'm going to do is the following. I'm going to define something called a boundary map. Okay? So the boundary map is something that sends I chains to I minus 1 chains. And I'm going to denote this map delta I. So it takes I chains into I minus 1 chains. And it's given by the following thing. So what do I need to do? What I need to do is, well, this is going to be a linear map, right? Because these guys are vector spaces, and so if I want to define a linear map, I just have to tell you what to do with the basis vectors, and then you extend by linearity. So what am I going to do to a basis vector? Well, a basis vector is one of these E sub a bunch of things where, because my face is supposed to be I-dimensional, it should have I plus 1 indices. Right? So I'm going to call the indices A1 up to I plus 1. Okay. And what I'm going to do, I'm going to write something and then I'm going to explain why this makes sense. It's a summation from j equals 1 to I plus 1 of the following thing, minus 1 to the j times E sub what happens when you take the jth guy off. Okay. So what on earth am I doing here? And I think that the best way to understand it is by seeing what the name of it is. So this is called the boundary map. And what I'm doing is that I'm taking a simplex and I'm mapping it to its boundary. So why is it that this picture does that? Let's see an example. For example, what's delta 2 doing to E of A comma B comma C? Well, you should think that E sub ABC represents this guy. Okay. And what am I doing? Well, I'm telling you that I'm mapping this guy to the boundary of the triangle. So what's the boundary? Well, if you look at this, what this is saying is go down the list of all the indices. Okay. Oh man. It's a little puddle of cleaning liquid there. So I'm supposed to go through all the indices from 1 to I plus 1. So every single index. And then I'm supposed to put some sign and knock off one of these guys. Okay. So first I take the first guy, A. So I put it with a minus sign. And then I knock off A, so I get BC. Okay. So I get minus BC. Because I knocked the first guy off, then I knocked the second guy off, and so I get a plus sign, and I get AC. And then minus, and I knock the third guy off, which is C. And I get AB. Okay? And so if you look at it, what this is basically the boundary of the triangle, right? The three boundary edges with some signs. Okay? Okay. So this defines a linear map from the I chains to the I minus 1 chains. Okay? If you look, for example, at what I would get with a tetrahedron, I would apply delta 3 of a tetrahedron, and I would get an alternating sum of the four faces of the tetrahedron. Question?
So the way you write that line taking BC is
right. So this is kind of, that's a good point. So the question is, how does this match this, basically? And so basically, maybe I'll put this in quotation marks, but really what I mean when I write this is that delta 2 of E sub A comma B comma C. And you see I very quickly get tired of putting these little brackets everywhere, so I just write ABC. And so this is E sub BC plus E sub AC minus E sub AB. Okay. And so this is the equation. Delta 2 of this is equal to this. Okay. So this is the real equation, but this is the way you should think about it. That basically, for each simplex, I'm mapped to the boundary of the simplex, and I get some signs that maybe are a little mysterious, but I think you'll see in a second why I want the signs. Okay?
How do you decide the possible order? How do you decide the plus sign?
The plus or the minus sign is determined by this minus 1 to the j. So it just alternates. So I take the first guy off, and that comes with a minus sign. That's A. Then B comes with a plus, then C comes with a minus, then you just go minus, plus, minus, plus, minus, plus. Okay. So that's some map. Where do
But I mean, I guess you have to agree on an order and cyclic and on your AI.
Yeah, so that's right. So I should have said that I'm doing this assuming that A1 is less than, etc., is less than AI plus 1. And so here I'm doing this assuming that A is less than B less than C. That's right. Okay. So that's my map from CI to CI minus 1. And so here is one of the most important observations. It's the following, that if I take the composition of the I minus 1 map and the I map, I get 0. Okay? So if I take the boundary of the boundary, I get 0. And maybe this is mysterious to you, but we're going to prove it. Now, of course, if you think about it intuitively, it doesn't make sense, right? Because you start with maybe a d-dimensional thing, then the boundary is a d minus 1 dimensional thing, and the boundary of that is a d minus 2 dimensional thing. So it looks like it should be something d minus 2 dimensional. But the point is that the minus signs were inserted in such a way that even though it looks like you're going to get a d minus 2 dimensional answer, everything is going to cancel out, and you're just going to get 0. And that's what I'm going to show you. Okay? And you can see it here, for example. What's the boundary of BC? It's C minus B. No. B minus C. The boundary of this is B minus C. The boundary of this is A minus C. The boundary of this is A minus B. And if you do minus B minus, well, whatever I just said, I'm going to get it wrong. If you do that, you're going to get 0. Just because of the way I chose the signs. And this is a general phenomenon. Okay? And this is a proof that is kind of, you just have to do it. And you should do it at least once in life, so let's do it. We just compute. So, well, this is a linear map, right? By the way, this map goes from where to where? But like we said, the input of this thing is I chains, and the output is I minus 2 chains. So this guy maps Ci to Ci minus 2. And so to show that the map is 0, I just need to show that every basis vector gets sent to 0. So let's just go ahead and compute that. So d I minus 1 delta I of a basis guy that, I mean, this is where notation gets annoying, but so I'm just going to drop the brackets, okay? And I think I'm going to write a lot bigger so that the subscripts show up in the video. So okay, I need to show that that's 0 for any a1 less than, etc., less than ai plus 1. Okay? So I just plug in. So delta I of this guy is summation from j equals 1 to I plus 1 of e sub a1, etc. Then I drop the jth guy. And then I go to ai plus 1. But I get that with a sign, right? Which I forgot. So summation from j equals 1 to I plus 1 of minus 1 to the j times this guy. Okay? Now, this is a linear map, delta I minus 1, which means that I can make it commute with the summation. So I can just take summation from j equals 1 to I plus 1 of minus 1 to the j times whatever delta I minus 1 does to e sub a1 up to aj up to ai plus 1. So what's this? Summation j equals 1 to I plus 1 minus 1 to the j. And then what I'm going to do is that I'm going to sum over k of basically knocking off the kth term here and putting a sign there. Okay. Now, I need to be a little bit careful, and I'm going to distinguish two cases. So I basically need to do this for k from 1 to I plus 1. And different from j, right? Because I need to let, first I take off the first term, then I take off the second term, then etc. But then I don't take the jth term off because that's already off. By the way, you guys remember this notation, right? I've been using it throughout the whole time. So whenever I put a hat on the variable, that means that that variable is not there. Okay? So I need to take the summation over k from 1 to I plus 1 and all the k's different than j. Okay? But I'm going to do that in two steps. First, I'm going to do it for the k's less than j, and then I'm going to do it for the k's bigger than j. Maybe you see why, or if not, you'll see why in a second. So let's do this, and then let's do plus the same thing. Okay, bigger than j. So what do I do here? I take off with a sign of minus 1 to the k, I take off the kth term, right? So I get e sub a1, then I take off the kth term, then I take off the jth term, and then I take off nothing else till the end, right? And then here I do the same thing, but now, I mean, here k will appear before j, here k is going to appear after j. So this is what I get with a sign. And you see that this is, the sign is the reason why I separated it into two sums, because even though this guy is a sub k, it is now the k minus first term in this list, because this guy is not there. So the sign that I assign to this guy is not k, it's k minus 1. Because this j offsets it. So I get this big thing. Summation of minus 1 to the j times this big bracket. Okay? Any questions so far?
So when we do this, we are only summing over things that are there. In other words, we're not, if we had like the fifth term, but we're missing 2 before that, then we're actually dealing with the third term.
Sorry, can you ask that question again?
The question is, so we are ignoring, say if I have the fifth term in my sequence, my basis, and 2 of those previously aren't actually there in this particular case. So in this case, you have j removed. So in any case like that, where we are just counting for the ones that exist rather than the ones that are total possible.
Yeah, exactly. So just to paraphrase what you said, basically what you're saying is that when here, I'm taking off the kth term. Sorry, I'm taking off a sub k, and I need to figure out what sign I need to give to that guy. And it alternates from this one. So it starts minus, plus, minus, plus, minus, plus. And what you do is that you count how many guys you have up to now. And up to now, you have, it looks like you have k guys, but you already took 1 out. So that means that from here to here, you have k minus 1 guys out. You have k minus 1 guys in, which is why you have to put minus 1 to the k minus 1. That's where that sign comes from. Okay. So what kinds of things appear? Well, we know that this map took I chains to I minus 2 chains, and so it makes sense that everything we see here is an I minus 2 chain. Okay. Now, what kinds of I minus 2 chains appear? Well, they're exactly the chains that you get when you take the chain from 1 to I plus 1, and you take off 2 things. Okay. And so let's just sum over all, and actually, let me just change the letters here. So each term like this is going to appear over here, right? For every r less than s less than or equal to I plus 1, greater than or equal to 1. But if you think about it, it appears twice, because we could have gotten this term in 2 ways. First by removing s and then r, or first by removing r and then s. So they appear twice. So the coefficient of this guy is something involving 2 things. Okay? So what do I get when I obtain it in this way? When I first took out s and then I took out r. The sign that I get is minus 1 to the s times minus 1 to the r. And what do I get when I obtain it in this way, where first I took out r and then I took out s? I obtain minus 1 to the r times minus 1 to the s minus 1. And so basically this is just 1 plus minus 1. So that means that this is a big fat 0. Every one of these terms goes to 0. Okay? So since every basis element gets sent to 0, that means that this is the 0 map identically. Okay. Does that make sense to you guys? Is that good? So if the signs seemed a little mysterious to you here, hopefully this proposition justifies them. Okay? If I put plus signs for everything, then I would not have this proposition. And you might remember that this is a very nice condition, because this condition of taking a composition of this times this equals 0 is exactly the definition of a chain complex. Okay? So this proposition is basically what allows us to do homology theory. So how does that go? By the way, I should tell you that when you do this in a topology class, and maybe you prefer thinking about it in this way, I mean, it's good to go back and forth. Sometimes you don't necessarily keep this convention of ordering the numbers. What the conventions that you keep are like these right-hand rule conventions, where you just, for each triangle, you give it an orientation, and it's up to you whether you're right-handed or left-handed. Okay? So this simplex, we might decide to order it like this, which I guess is if you're right-handed, or we could order it in the other way, which is if you're left-handed. You make that convention ahead of time. Okay? And depending, I don't know what convention I just used, but depending on the convention that you used, the boundary of ABC would be AB plus BC plus CA. But now CA is minus AC because it's AC backwards in the wrong orientation. And so all of these signs actually come out very naturally if you make these conventions, for example, for a tetrahedron. For a tetrahedron, if you think about it, there are also two ways of orienting it, and it's just according to whether you're right-handed or left-handed when you read A, B, C, D. Okay? So if you think about it from that point of view, the signs come up naturally. So I think what I did is left-handed convention here, right? Because I'm getting minus BC, which is backwards, then plus AC, which is minus CA, and minus AB. So this is exactly this convention. The boundary of this guy is AC plus CB, which is minus BC, plus BA, which is minus AB. So that's another way that you can think about these signs. It's just kind of what comes naturally from these sign conventions. Okay. All right. So like I said, once you have this composition that applying the boundary map twice gives you 0, you can define a chain complex. And this is kind of funny because this has two names, either the augmented or the reduced chain complex. It seems to me that these words kind of contradict each other, but and what we have is basically something like this. So we can just list all the chain. These are generally called chain groups. I've been calling them vector spaces because we've been doing this over a field. Okay. So I take the vector space of -1 chains, the vector space of 0 chains, and so on. And then I have maps going all the way over here, given by these deltas, right? So I have a map from D-1 to D-2, and that map is called the boundary D-1. I have a map from C1 to C0, that's called boundary sub 1. I have a map C0 to C-1, this is called delta 0. And this is just everything maps to 0 here, and 0 maps to 0 here. So this is the chain complex. Augmented reduced chain complex. And if you remember, we encountered this when we were doing these free resolutions. Now, in free resolutions, we demand more because we demand exactness at every step. And here I'm not demanding exactness. Right? Now, if you remember, the homology basically measures how not exact you are. So I defined this in the previous context of just abstract chain complexes. Okay? But now I'm going to define the homology to basically be the homology in the same way that I defined it back then. So what it is this. So let me just make a couple of, of course, what you should be thinking of is that we have here we have Ci of delta, which maps to Ci minus 1, and which is mapped to from Ci plus 1, right? And this continues over here, and this continues over here, and these maps are called boundary. By the way, sometimes you'll see that people just drop the subscripts because you can tell the subscript here has to be I because this is I. So if you don't see a subscript, just fill in the natural subscript that makes sense. So let me just remind you how this goes. We just proved that delta I of delta I plus 1 is 0. Okay? That means that if you take something here in Ci plus 1, and if you map it over here, and then you map that over here, you get 0. Okay? So what I'm saying is take something here. When you map that over here, what you get is everything in the image of the map delta I plus 1. And what I'm saying is that all of those guys are in the kernel so that they go to 0. Okay? So this is equivalent to saying that the image of delta I plus 1 is contained in the kernel of delta I. And you guys remember that the condition of being exact is exactly the condition of this being an equality. If this is equal, then we are exact at Ci. And if it's not equal, then the homology measures that. You have a question, Steve?
Yeah, so in the exact sequences, another condition is that all of them, one of the maps is surjective and one is injective. That's not the case here, right?
So your question is that when we defined exact sequences, we wanted to be exact here, and that meant that this map is surjective, is injective, sorry. And we want it to be exact here, meaning that this map is surjective.
Yeah.
And that might not be the case here. And so we have to measure that also. But basically, you can just define delta D to be the 0 map here, delta minus 1 to be the 0 map here, and you don't have to do anything differently. So we defined the homology to be the measure of how much you are not exact. Or let's say how close to exact you are. Okay? So if the homology is 0, that's because you have equality here. But in general, the homology is just this quotient. Whenever you have a subspace or a vector space, you can take the quotient. Okay? And this basically tells you whether you're exact or not, and if you're not exact, then how bad is it? Okay? So this is the reduced homology, the reduced ith homology of delta. Okay. And just to give you a couple of names of things that maybe you'll see in other books, sometimes this receives the name of bi of delta, and this is called the boundaries. The elements of bi of delta are called boundaries, and this guy is called zi of delta, and the elements are called the cycles. Okay? And so the homology is cycles mod boundaries. Okay? Now, like I said, I want to define these things for two reasons. First of all, because that's what some books use. But second of all, because these offer a very good intuition for what's going on here. I mean, think about this. Why are we calling bi of delta the boundaries? Because something that lives here is an I chain, so it's a sum of I simplices. How do you get to live here? You get to live here if you come from here. The things that are here are the I plus 1 simplices. And what this map does is that it takes an I plus 1 simplex and it takes the boundary. So that means that you get to be the image of something here if you are the boundary of I plus 1 dimensional faces. Okay? And you get to be in the kernel of this guy if the boundary of u is 0. Okay? And you can see that basically what happens is that the boundary of a cycle is 0. And this is why this is called the cycle space. We'll see this very concretely in an example so that you see that these names are very, very close to what we see in the pictures. Okay? But so this is homology right here. Okay? So do you guys have any questions about the definition? Yeah.
Can you be more specific about what you mean by cycle?
So the way that I want to be more specific about this is to show you an example. And I think with an example, you'll see exactly what I mean.
What's the word under
This word is cycles. Maybe now it looks a little bit more like cycles. Maybe. Zi of delta is cycles, bi of delta is boundaries. But let me just draw a very rough picture here, which is that what I mean by cycles is something like this. Okay, looks like a cycle. And what I mean by boundaries is you take an actual triangle and you take the boundary of it. So this is a full triangle and you take the boundary of it. Okay? And so what I'm telling you to do here is consider all the cycles and subtract the ones that are full. Yeah? So what I'm telling you basically is look at the holes of this thing. What's a hole? A hole is something that you can go around but that is not full. So this is the intuition for why this is basically holes. Okay? So it's just like this mod this, and so again, let me put quotation because this is intuition. Is not exactly. I mean, you have to do some work to make this precise, but this is the intuition that you should be thinking of. Then this is I-dimensional holes. Okay. And while I do the example, I want you to think about what that might mean for a hole to be. What's the dimension of a hole? Okay. But what I want to do is just compute the homology of this guy for the rest of the class. But let me ask you actually, so what should I get looking at this picture? Think about it. What should the homology of this thing be? In other words, how many holes does it have? For example, how many two-dimensional holes does this thing have? I guess you mean this one. This is actually one-dimensional. We'll see why. Now, let me ask you something. So I think we agree that there is exactly one hole of this dimension, which I'm telling you is one dimension. So how would you see that then? Here, what do you expect this guy to be? To indicate the fact that I have one hole. Do you expect to have a number 1, or what do you expect to see here? This is a vector space, right? And so this answer should be a vector space. And the 1 is indicated in just, vector space is f to the something. And so we expect this to be f to the 1, hopefully. So we'll see that that's true. But before we do that, let's just compute everything, basically. So for example, I don't know, let's see what's... Let's start by computing this guy. So this is supposed to be cycles over boundaries, right? So what are the cycles and what are the boundaries? So what is this and what is this? Which one would you rather give me? B, right? B is easier. Because the boundaries are just, you take everything that lives in C2 and you take the boundary of it. Okay. By the way, so remember that C minus 1 of delta is the span of E empty. C0 of delta is the span of EA, EB, EC, ED, EE. C1 of delta is the span of the edges, right? So EAB, EAC, I have to be careful because I should only have things in my picture, right? EBC, EBD, ECD, and then C2 of delta is the span of EABC. So just to know where our things live. So Z1 of delta, that is the image of C2 of delta. So I take everything in C2 of delta and I take its boundary. Okay. Well, here I only have one generator here, so I just need to take the boundary of that guy. So this is B1, sorry. So B1 is the span of the boundary of this guy, which we saw is minus EBC plus EAC minus EAB. Okay? So that's not too bad. Now, Z1 of delta is a little bit trickier because what we have to do is look for all the things that live in this space, right? They're combinations of edges, such that when I take the boundary of that thing, I get 0. So what does this look like? This is basically the things of the form alpha EAB plus beta EAC plus gamma EBC plus delta EBD plus epsilon ECD, such that we call this F. The boundary of F should be 0. Which boundary? Boundary 1. Okay? So what's the boundary of this guy? Well, we have to compute it. So boundary of alpha EAB is alpha times EA minus EB, right? Boundary of BC is this minus this. Boundary of BC is EB minus EC. Boundary of BD is EB minus ED. And boundary of CD is EC minus ED. Okay? And I need this to be 0. Right? So what I'm after is I need to find the alpha, beta, gamma, delta, and epsilon such that when I compute this big thing, I get 0. So it's a little bit tricky, but we can do it. Why is that? Because this involves an EA term, an EB, EC, ED terms, and each one of these terms is going to have to be 0, right? So the things involving EA have to give me 0, things involving EB have to give me 0, etc. Okay? So, for example, if I want this to be 0, then what should beta be? I don't really have a choice. Because if I have an alpha here, I must have a minus alpha here to cancel it, right? So let's just save marker here, and instead of writing a bunch of equations, let me just put a minus alpha here, because that has to be minus alpha. Anything else that I can conclude here? It looks like delta and epsilon have to be opposites of each other because of the ED. So let me just take this guy and call it minus delta. Anything else that you see? What should gamma be? I need minus alpha plus gamma plus delta to be 0. So gamma is going to have to be whatever cancels that. Help me not make a mistake here. So I guess I need alpha plus delta. Is that right? Alpha minus delta. Gamma needs to be alpha minus delta for this to be 0. And this checks out. If you choose any alpha and any delta, and you compute this, you get 0. So what that means is that these are the things of the form alpha EAB minus alpha EAC plus alpha minus delta EBC plus delta EBD minus delta ECD. I can choose alpha and delta to be anything, and this is going to be mapped to 0. So alpha and delta are in my field. Okay? So these are the things that map to 0. I think this is going to be a little bit nicer if I write it as the span of something. What is this the span of? Well, what I have here is a combination of alpha times EAB minus EAC plus EBC, and then delta times minus EBC plus EBD minus ECD. Okay. These are exactly the things in the span. And now hopefully you see why I call them cycles. Because this guy, EAB minus EAC plus EBC, is exactly what I get walking around here. And minus EBC plus EBD minus ECD is exactly what I get when I walk around here. And these are my two cycles. So what do I get for my homology? Well, I get this mod this. Right? Now, this guy is exactly this guy with a minus sign. Right? And so you see what I'm saying is exactly what I had over there, right? These are the two possible cycles that you might have. But I want to mod out this one because this one is full. So I have two cycles, A, B, C, and B, C, D. So those could be holes, but then I have to see whether they are holes or not. And this one is not a hole, so I mod out by it. And what I get is that this mod this is generated by minus EBC plus EBD minus ECD, which is the hole. That is the hole that you guys told me I should find. Okay? And so that means that this guy is exactly f to the 1. And not only am I getting the right dimension, but actually, if I look exactly at what the elements are that live in here, they are exactly the holes. This is the hole that I was looking for. And so this is what I was telling you, that basically we want the algebraic machinery to do the searching in the geometric picture for us. Okay? And this algebraic machinery works out beautifully so that in the end it exactly finds the hole that we were looking for algebraically. Okay? So that confirms that. And I'd like you guys to really practice with this. So you should compute the rest of the homology. Right? Because when you do this, you need to do it for every I. And so I really would like you guys to do this example, and let's talk about it in the forum so that you can see how many holes there are of every dimension. Presumably from here on you should get 0, right? Because there aren't any bigger holes. But maybe here there are other things. So you should just carry out these computations, and then we can talk about what they're saying in terms of the topology. But I also hope that you're seeing how this stuff, it's like I was telling you, we don't get to choose. Now this is topology, but this looks almost exactly the same as our free resolutions. It's just that before we had polynomials and now we have topology. But in the bottom, actually, it's basically the same thing. That's what we will prove next time. All right.